You type one command, kubectl apply -f deployment.yaml. Enter. Done, right? Wrong. That command did not create your pod. It did not even talk to your pod. What actually happened is a relay race through 6 independent systems that do not trust each other, do not talk to each other directly, and have never even met. Today we are going to follow that one request, hop by hop, and by the end you will understand why kubectl apply is one of the most misunderstood commands in infrastructure. Before anything leaves your laptop, kubectl does something sneaky. It is not just uploading your YAML. According to Kubernetes' own documentation on declarative object management, kubectl apply performs a 3-way merge. It compares your new manifest, the live object currently in the cluster, and a hidden annotation called last applied configuration, which it stashed on the object the last time you ran apply. That third piece is the trap. If you delete a field from your YAML while using classic client-side apply, and that field was never captured in the last applied annotation, kubectl has no way to know you want it gone. It just leaves it. This exact failure mode is why the Kubernetes project built server-side apply, which moves the merge logic into the API server itself and tracks per field ownership through something called a field manager, so multiple controllers editing the same object do not silently clobber each other. Only after that merge is computed does anything hit the network. The request lands on the API server and walks through authentication, then authorization, then admission control. Admission is the part almost nobody pictures correctly. It is not one gate, it is a pipeline. Kubernetes official docs are specific about the order. Every mutating webhook runs first, in sequence, and any one of them can rewrite your object, inject a sidecar, or set a default before validating webhooks ever see it. Only once mutation is finished do the validating webhooks run, and they run in parallel, so multiple policy engines can check the same final object at once without waiting on each other. None of this has touched ect yet. Your pod could be rejected right here, and it would be as if it never happened. If admission passes, the object gets written to ect, and this is where the myth that Kubernetes just stores state in a database undersells what is actually happening. Ect is running the Raft consensus protocol, which means a majority of ect members have to agree before your write is considered committed. That has a hard ceiling. Kubernetes' own scaling documentation says a supported cluster tops out around 5,000 nodes, 150,000 pods, and 300,000 containers, and ect's default recommended size limit is 8 gigabytes. That is not arbitrary. Kubernetes actually switched its default storage backend from ect version 2 to ect version 3 back in release 1.6, specifically because version 2 could not survive write load at 5,000 node scale, according to the Kubernetes project's own blog. And that ceiling is real enough that when OpenAI wrote publicly about running Kubernetes clusters at 7,500 nodes, they reported their API servers were holding up to 70 gigabytes of heap each, and they dedicated 5 separate API servers and 5 separate ect nodes just to spread that load, so one bad day did not take the whole control plane down with it. Google went further. InfoQ reported that GKE pushed a cluster to 130,000 nodes, and the only way they got there was by ripping ect out entirely and replacing it with a data store built on Spanner. The lesson under the hood is that ect's limit is not a law of physics. It is an architectural choice, and at a certain scale, everyone eventually rebuilds around it. So your object is committed. How does anything else know? Not through polling. Kubernetes components open long-lived watch connections to the API server and get streamed events, added, modified, deleted, each tagged with a resource version, so a client that drops and reconnects can resume exactly where it left off instead of relisting everything. This is the list watch pattern, and it is a big part of why a 5,000 node cluster does not fall over just from components checking on each other. One watch, many events, instead of thousands of components hammering the API server every second asking if anything is new. One of the things watching is kubescheduler, and it only cares about pods with no node assigned yet. It runs every pending pod through 2 strict phases. Filtering first. Does this node have the CPU and memory? Does it tolerate the node's taints? Does it satisfy affinity rules? Any node that fails even one check is dropped immediately. Then scoring. Only on whatever nodes survived filtering, ranking them by factors like resource balance, and binding the pod to the winner. The scheduler does not create anything either. It just writes one field back into the API server, an assignment of pod to node. That is the entire scheduling step. The kubelet on that node is also watching. And here is the part that trips people up the most. Nothing tells the kubelet to go start this pod right now. Kubernetes' own docs describe it as a sync loop. The kubelet keeps a local view of what pods should be running on its node, and on every loop it compares that view to reality and reconciles the difference on its own schedule, independently for every pod. When it decides a pod needs to start, it talks to the container runtime over a gRPC API called CRI, over a Unix socket, first asking the image service to pull the image if it is not cached, then the runtime service to build the pod sandbox, set up networking, and start the containers in order, init containers before app containers. This path has gotten real engineering attention. Kubernetes 1.27 specifically shipped changes to stop the kubelet from polling the container runtime for status and switch to event-based updates instead, specifically to cut pod startup latency. So walk back the whole chain. Your laptop computed a merge. The API server ran a gate. Ect ran a vote. A watch fired. A scheduler placed a bet. A kubelet reconciled a loop. Nobody ran your pod. 6 systems, each reacting to the last one's decision, converged on the state you asked for. That is not a command. That is a conversation. And once you see it that way, half of what looks like Kubernetes flakiness stops being mysterious. If this connected the dots, subscribe. Compile goes under the hood of one system like this every single day.